Let's look at OpenStack's University Physics Volume 2, Chapter 8, Problem 65. An air-filled or empty parallel plate capacitor is made from two square plates that are 25 centimeters on each side and 1 millimeter apart. The capacitor is connected to a 50-volt battery and fully charged. It is then disconnected from the battery and its plates are pulled apart to a separation of 2 millimeters. A. What is the capacitance of the new capacitor? B. What is the charge on each plate? And C. What is the electrical field between the plates? So let's write down the knowns and unknowns. There's lots of things we know. So the area of the capacitor is 25 centimeters by 25 centimeters. And that is 6.25 times 10 to the negative 2 square meters. Then we know that initially the capacitor plates are 1 millimeter apart. And the capacitor is connected to a 50-volt battery and fully charged. We also know that it's air-filled, so that means that the dielectric constant is 1. There's no dielectric between the parallel plates of the capacitor. Then we're disconnecting the capacitor and moving the plates to a distance of 2 millimeters apart. In part A, we're looking for the capacitance of this new capacitor, so I will call it C2. In part B, we want to know the charge, and in part C, we want the electric field. So here is the capacitor. This is, I'll call it C1, and then once it's fully charged, we're going to pull the plates apart. So this distance is D1, and this will be D2. All right. So in part A, we're looking for the capacitance of the new capacitor, and we know that capacitance is K epsilon naught A over D, and this is the capacitor where the plates are 2 millimeters apart. Dielectric constant is 1, then epsilon naught is 8.854 times 10 to the negative 12th. Area is 6.25 times 10 to the negative 2 divided by 0.002 meters. And the capacitance then is 2.77 times 10 to the negative 10th farads. All right, in part B, we want to know what the charge is. Now, the trick to this problem is to know that once we charge the capacitor to a certain voltage, so we connect the voltage across it, we charge it, then we're placing charges Q on the capacitor. So we have plus Q here and minus Q there. Now we're disconnecting it from the power supply, and that still leaves plus Q and minus Q on here, no matter how much we pull the plates apart or bring them back closer together. The charge still stays the same. It doesn't leak, we assume. So it just will stay the same on the capacitor. So how do we find the charge? Well, we can use Q equals CV, but we know that the voltage was only there when the capacitance was C1, meaning that the capacitance 1 was when the plates were 1 millimeter apart. So then I will have to write this as dielectric constant epsilon naught A over D1 times V, and that is 1 times 8.854 times 10 to the negative 12th. Area is 6.25 times 10 to the negative 2 divided by D1, and that's 0.001, and the voltage is 50 volts. So the charge then is going to be 2.77 times 10 to the negative 8th coulombs. Then in part C, we want the electric field, and we know that the electric field between capacitor plates is sigma over epsilon naught, where sigma is the surface charge density, so that would be Q divided by A over epsilon naught. So that will be 2.77 times 10 to the negative 8th that we found in part B, divided by the area 6.27 times 10 to the negative 2, epsilon naught 8.854 times 10 to the negative 12th. And this gives us 5 times 10 to the 4th volts per meter.